looks good to go. All right, let's post some places, let people know we're doing the thing. Let's get stuck into some more stuff. So welcome back to anybody who joined us for previous episode or is watching this live. Doing some more work on UNets today. Let me put the post out, see if we can bring anybody along. All right. Good. All right. So what are we doing today? There's a couple of things. So I've done some work on this UNet stuff that we worked on in the last stream. If you haven't checked that out, there is a part 1 to this. We went through the original UNet paper. We built a pretty simple version of the UNet in PyTorch. And this series overall is going to look at some more recent advancements in the world of UNets. This week, in particular, ResNets, as you can see here. And we're going to work our way up to some more complex stuff. My goal is that eventually we should be in a position to replicate some of the work from something like Stable Diffusion. So ResNets will be a little part of that. We'll look at attention in a future stream probably. Then some conditional UNets to make the output a little bit more interesting and blend in some other data. And there'll probably be some streams in between where I do some weird and boring stuff like just tweak stuff and all of, I guess, the nitty-gritties of the AI world, the realities of it all. But before we dive into ResNets, what they are, and how we stick them in the unit that we built, I just want to take us through some of the stuff that I've done since last time we caught up. What a funny premise. Anyway, so the code is on GitHub. The link is in the video description if you're after it. I will update it at the end of all the streams, just so that you have the latest and greatest. The version in Paperspace, which is also linked there, is slightly newer and will, I think, be somewhat live. I'm not really 100% sure how the public projects work on Paperspace, but you can tell me and we can learn together. And the other thing you can check out, which has a link in the bottom, which you should be able to access, is a weights and biases project for this work. You can see I've got some stuff here plotting from what I called the original model. That's what we worked on last time. I'll go through that. And then I've also got a little scratchpad project, which is just stuff that I'm trying before it's ready to be put up on stream. But anyway, let's get into some of those changes, and then we can talk what we're going to be adding in this this stream. So, looking at the notebook from last time, V0, I did some basic weights and biases stuff. If you don't know what weights and biases is, it's a tool. There's a number of them out there. This one's pretty good. That lets you log things like your loss and other metrics to a dashboard and compare runs and do repeatable experiments. It has a ton of features that I'm not yet using, but I figured I'd start with these and we could build that up over time. So because of the way that Paperspace runs, every time you reboot the machine, you do need to reinstall it and grab the API key again, which is something that I'll need to work out how to do off camera, but we can work that out together. And yeah, so that's basic. But the other thing that I did is I created this new Python file called common, and that has a lot of the data loading stuff in it, the train loop, the test loop, things like that. And the reason I did that is so that as we create, V1, V2, V3 for all the UNet stuff, we can just focus on changing the actual model and make sure that we're running it against a pretty common set of functions for training and testing and things like that. Because the goal here is to compare how these more advanced UNet models compare to previous ones. as we add more and more stuff to them. So we'll go through that file in a sec, but you'll see this is all the stuff we worked on last time. If you have watched the stream, you know all of what's going on here. And then I set up some weights and bias stuff. I'm going to group them in one sort of group per stream. So as we start to make changes, so this new version that we create soon will be in the ResNet group. And then some minor changes here, passing the weights and biases object in and keeping track of the step, just so that it can log the steps correctly against weights and biases, especially as it does train and test in there. One thing I haven't put back in or moved to weights and biases, which we might do early on here, is the image logging stuff. It at the moment is just logging metrics, but that should be pretty easy to add. So common.py itself, which I will add to the GitHub repo, it's got our data loader, a few transforms in there, just the same stuff as last time. Just grabbing from the Oxford 3T PET dataset. I have had a look at the VOC dataset as well. I might switch over to that because it's got more classes and I think a little bit more data, but this will do for the minute. Does a train test split, as you might expect, just a 80-20 split at the moment. Not configurable because it's good enough for what we're trying to do here. I found a good implementation of what's called dice loss. Really what I wanted was the dice metric. We'll talk about that in a sec, but this Kaggle notebook, which you should check out and give a thumbs up to or an upvote or whatever they do on Kaggle, has a bunch of loss functions for people to use in their code. So I grabbed this dice one, and that allows us to log to the weights and biases, the dice function. The other thing I did in here, I've got our train loop from before. I added optional data augmentation. So I ran a few versions of the previous model that we'd built. It tended to overfit quite badly. I think for a fair comparison, we should do some basic augmentation. So the way this works here, it does it on the whole batch because realistically it doesn't make much difference if we do it per image or per batch, given that we do 50 odd epochs. There's a 50% chance that it'll left-right flip the image and the corresponding labels naturally. Then it also rotates the image. I found a bug. There you go. So it rotates the image by a random amount. What I just realized is it should also rotate the labels by that same amount. So one of the reasons that I'm doing augmentation here and not in the data loader is because for segmentation, we'll just go in here for a sec. You have, let's say you have your image of whatever, you know, your cat or whatever. It's not too bad. And then you've got your similar image, which is your label. Let's say this is just a very basic label. If we do data augmentation on this image, let's say we shift the image or something like that, but don't shift the label, it will not line up anymore, as you might imagine. And if you use the transforms in this format, it applies a different set of transforms to the images and to the targets. Now you might be saying, okay, why don't we just do random rotate, random scale, random whatever on both? And the reason for that is that the random value that it uses to rotate is not shared between these two sets of transforms. It looks like my screen has once again frozen on Excalidraw. Let me see if I can get that back. This macOS screen sharing is not doing too well. Just switch back and forth. Okay, that seems to be back. Yeah, sorry. So if you're doing it in these transforms here, it uses different random numbers for the rotation, so your images and things become unaligned. So we do it down here in the training loop. So we've got left-right flip, random rotation between -15 and +15 degrees. So just a small rotation there. And then for the images themselves, we sort of randomly alter the brightness between 0.9 and 1.1. And I found that helps with the overfitting. I wonder whether this error, not rotating the labels, is going to have much of an effect, but we will soon see. So the other differences here is if weights and biases is being used, it'll log the loss. It still prints the loss every 5 batches. And similarly in the test loop, it logs the average loss and average dice coefficient for the entire eval set once per epoch. This is where the image logging was. I might actually just, for the sake of this stream, put that back on because it's handy to have a look at what it's learning. But that's the differences we have there. So let me do a couple of things. Number one, let's just run this. We'll start this running again, and we will see if that rotation made any difference. Now, I'm just going to very quickly just change to just my face so that you don't, I don't know if it'll be doxing, but don't dox my API key as I log into weights and biases. Now, the project should be public, so you can see all of this anyway if you use the link that is in the video description. Oh, what's going on here? Yep, cool. And paste the API key. And good stuff. All right, we can go back to showing my screen now. Then I'm not going to get doxed. I don't know really how much damage you could cause by having my weights and biases API key, but anyway. Now we'll go through here. Again, this is the model from last week. We'll just start it running again in the background. I'll show you some stuff around weights and biases if you haven't used it before. It's quite cool. And then we'll start talking about some of the stuff we're doing this week. So, the other thing I did is I bumped up the learning rate. I found that it was learning very slowly before. I just tried a bunch of different learning rates. There was no fancy hyperparameter optimization there. It was just me tweaking a bunch of them. All right, so let's run through this. Now, this should print the images. I did uncomment that code. I didn't really check that it was correct. So I modified this a little bit as well. Before, it was overlaying the labels on the picture. And what I realized is that in dark parts of the image, you'd get something that looked like it was not getting the label correct, but it's just how it was doing alpha blending. So instead, I've got this contouring function running, and that sort of marks the 50% mark and where it starts to think it's a pet versus the background. Now, mind you, this is step 0, so it is just sort of random initialization segmentation at that point. But we'll see it gets a little better as we go along. Now, let's talk about weights and biases. So let's pull this up, and it should start to show the different groups. So if we come into this group, which is the one we're running now, we can have a look at what this is all about. So the way it works is every time you start a run in this notebook, it'll create a new run here in weights and biases. And it'll log any metric you tell it to log. In this case, we've got the loss, the eval loss, and the dice. You can log images, you can log audio, you can log text. It's very cool. The other thing it will log, we'll have a look at the one that ran last time, is Whereabouts does it put that? It'll log things like GPU usage and things like that. So if you are remote monitoring a session, you can get that information. It will keep a lot of the output logs, so you can see all of the stuff that it printed to the terminal. It's got a bit of metadata. There is an overview of the report. It's got mins and maxes for values. I must have set the config parameters incorrectly. We'll fix that up as well because I was trying to log those so we could compare different hyperparameters. But you'll see at every step it'll log different metrics, and the value of this, if it's not immediately obvious, is you can compare runs. So if we have a look within the original group, we can compare the run that we did before, or the one that I did before the stream, which is this Still Bush 10, to the one that's running right now, which is Iconic Mountain 11. Now, I wouldn't imagine a huge amount of difference here between these two. It's a shame that they've picked colors that are so similar, but there was that bug in which it was not rotating the labels, so the dice may end up being a little bit higher. You can also set up things which I never use because I just don't need it, but you can set up alerts and things. So you can connect Slack or email and you can put in alerts if accuracy falls to a certain level or whatever else, and also get alerts if your thing crashes or finishes if you want, which is handy. So in a sort of, I guess, more professional context, some of the models that we used to train for medical image analysis, sort of more advanced versions of these units, they might take 2-3 days to train. And you'd really want to know if they crashed partway through, because you tend to start them and then go and do something else because you can't watch your logs for 3 days, or you shouldn't. You definitely can. It's quite addictive, but you shouldn't. So that's that. So we'll do a couple of things, but before we do, I'll just give you an overview about what the dice score is, because that's a handy one to have. My screen does not seem to like going to this Excalibur screen. This Mac OS window sharing thing is not excellent. Let's see. We could switch back and forth again. I'll come up with a better way to fix that before the next stream. Anyway, dice coefficient. So dice coefficient is a number between 0 and 1 that measures how good a segmentation is. And it compares a predicted segmentation to a real segmentation. And it's similar to another metric called the intersection over the union. And what that is, in this case, is if... Can I pick colors for these so that they're not all exactly the same? Yep, purple, we'll say, is our predicted. Let me just put a little purple. Yep, I'd say purple is our predicted and orange is our real label. Now, if in our, let's say our image is this. If in our image this was our prediction, you can kind of tell already that it's kind of crap. It's partially overlapping. It's gotten this area right, but it's not great. The more these two things overlap, the better it is. Now, if it's smaller, that's not quite as good as if it's the same size. And likewise, if it's too big, that can be bad. So the dice coefficient is calculated based on two different regions. One of those regions is the intersect between the predicted and the real label. Now that's this region here that's overlapping. So what you would do, and I'll show you the code after this, is you would calculate the number of pixels that are in this overlapping region. So where it's set to 1, let's say, in both images. What it then compares that to is then something called the union, which is the total area. Actually, I'll just remove that so it's not confusing. The total area that has any prediction in it. So in this case, it's this little laying down snowman type shape. And the ratio of those two areas gives us an idea about how good the segmentation is. Now, if these are two exactly the same circles, there's going to be 100% match between the intersection and the union, and you're going to get a score of 1. If there's no overlap, let's say it predicted something down here, or it predicted the entire image was blue, you're going to get a much lower score. I think, yeah, if there's no overlap, your numerator is going to be 0, so you're not going to get a dice score. And that's a dice score. And it's used as one predictor of how good a segmentation is. You'll see it in a lot of the leaderboards, and we're using it because you'll see it a lot, and it's pretty simple to implement. So coming to the code for a second, back to this common.py, this is one of the ones that we got from that Kaggle notebook. And so the way it does it here is with some tricks around having one-hot encoded values and being able to multiply and add them. But it calculates the intersection by multiplying the targets with the predicted value. Now, both of these are 1 for a given pixel. That's going to be 1 times 1 is 1. If either of them are 0, then it's going to be either 1 times 0 or 0 times 1, which will give you a 0, which means that if you sum all of that up, you get the number of pixels that have a 1 in matching areas between the images and the targets. The intersection, and this is a slight difference between dice and the intersection over the union. In the intersection over the union, you would calculate the actual union, so where 1 is set in either image. But in dice, what we do is we just say total number of pixels. So we sum the number of pixels set in the input and in the targets, and we calculate the division of those two. Now, you'll see this smooth factor here. That just really helps us stop dividing by 0. It does a little bit at the more extreme values, but its main purpose is that if you had 0 plus 0 on the bottom, you're not going to be dividing by 0. Now, in this particular instance, this is a loss function that's being used. So they do 1 minus the dice here because we're trying to minimize a loss. But when we log it in the eval loop, we do 1 minus here. So it's 1 minus 1 minus, which just gives us the dice score once again. So having a look at the weights and biases setup, you can see this is where it's logged the dice in both cases. And thankfully, fixing the bug made the dice score go up. It's not always the case. That's sometimes a sign that you've cooked your data pipeline. But anyway, so you can see here as we train the model, the dice score goes up, gets closer to 1. In the example where the labels and the and the images didn't line up in training, it never got above about 0.76. Now this dice is still technically correct because it's evaluated on the eval set and there's no rotation there. But as you can imagine, if we don't rotate both the labels and the image, they're going to improperly align, and training on that is not going to lead to a useful model. So we'll let this run, and you can see here as well, this is the training loss. You can see it gets pretty spiky, so what you might want to do is add some smoothing, which makes it a little easier to compare. As expected, aligning those images makes the loss a bit lower, and I would imagine that over time the eval loss will come down as well. But we're not here to talk about all this. We're here to talk about ResNets. We will have a look at this config thing as well as we go. But anyway, let's get into ResNets and what they are. So you probably heard about ResNets. Pre-trained ResNet models are pretty common. They come from this paper, which is available on archive which is from a group at Microsoft Research from late 2015, so it's pretty old now. And I encourage you to have a read of this. It's pretty easy to read. It's quite a well-written paper. But the problem that they're ultimately trying to solve here was characterized pretty well by this this graph over here. What they noticed is that the theory, which is that if you add more layers to your neural network, it has a better capacity to learn stuff and will get a lower error, didn't really hold up in practice. So this 20-layer model, which was just a traditional sort of conv net plus a fully connected net, it was a classification problem, performed pretty well. They added more layers and somewhat surprisingly, the error went up. And the hypothesis that they came to and the reason for looking at ResNets was that the more complex these networks are, the harder it is to properly optimize them. And they end up in these sort of suboptimal areas. You can still see it does learn, but it's not able to learn as effectively as its smaller cousin. So to combat this, they introduce this idea here, which is what they call a residual block. Now, the term residual and the concepts of residuals are a statistics throwback, which we won't get into. It's not really necessary to understand how these work. But effectively, it takes your sort of normal setup, which is some sort of weight layer, maybe fully connected, maybe convolutional in our case, your activations and so on, and then adds the original input to the output. And what this does is it constrains what these layers are learning to instead learn a slightly different mapping, which they call the residual, and their hypothesis, which has been shown and has been used many times since, is that deeper networks learn better with these sort of configurations. So if we have a look at the networks that they tested here, we'll then get into some implementation details. They have the old school VGG19. So pretty standard convnet. You got a couple of conv layers, some pooling, some more conv layers all the way down. Then you've got a couple of fully connected layers at the end. And in this case, maybe they had 1,000 classes. But anyway, number of classes right there at the end. So a few fully connected layers. They then made a 34-layer version of sort of VGG19 with a whole ton more conv layers, as you can see here, 34 of them, would you believe it? And then instead of these multiple fully connected layers, they did average pooling to get, and then pass that into one fully connected layer just to get it to the number of desired outputs. And then head-to-head with that, they build a residual version of this network. These little arrows here, now they're pretty similar to the skip connections that we put in our convnet, our unit, sorry, but they work on a smaller scale. There's two variants here, which we'll talk about. There's the solid line ones and the dotted line ones. When we implement this, I'll talk about the difference, but the reason that they need two is that if we are adding X to the output of this weight layer and the dimensions, the number of features in X is the same, we can just add them. You know, if you've got 64 feature channels and you're adding it to 64 feature channels here, it's easy. You just add channel by channel. If you are changing the number of feature layers between the start and the finish, let's say you're going from 64 to 128, you can't add 64 channels to 128 channels. So you need to do an additional step here to increase the number of channels to 128 and then add them together. The other thing that they mention in this, before we get into the results, is two different types of residual blocks. A fairly simple one, it's just got a couple of layers and then it's added on. And then on the right here, for some of their bigger networks, so ResNet 50, 101, 152, they propose this idea of a bottleneck building block. And so the important thing to know about the bottleneck is that when you're at the top of this and your data is coming through, in this case we have 256 dimensions. So we've done a bunch of convolutions, we've created 256 feature maps. These first couple of conv layers reduce the number of dimensions there significantly, in this case by a factor of 4, and then increase that number back up to 256. These two one-by-one convolutions end up being sort of weighted combinations. You can think about them that way. It's similar to the final layer in our UNet. Now this has a couple of benefits. One, from a sort of AI theoretical point of view, it forces it to learn better representations. From a practical machine learning engineering point of view, lower numbers of features means less RAM. But if you're a Google or a Microsoft, RAM is probably not your primary concern, but it can be helpful if you need to drop the number of features for any given reason. So, looking at the results, they kind of cracked their original problem. This is the plain network without the residuals, 18 and 34 layer variant. This is the ResNet variant. And you can see here the 34 layer one is in fact better. So that's good stuff. So what we're going to do now is we're going to add these ResNet blocks, to our network. So I've got a picture of them here, and we'll think about how we're going to add these in based on some other work. So I had a look at this GitHub repo. There's many different ways of doing this, is what I've found in comparing a number of these, because as you can see here, this is fairly abstract. It doesn't talk about batch norms or any other sort of stuff. And people put them in different ways. But we'll get into that as we go. What we'll do is we'll probably build a variant for each of these. Off stream, I'll run a number of experiments. They take a while. It takes about an hour to run the full set of experiments at the moment, so it'll be pretty boring just to watch the logs, but you'll be able to get them out of weights and biases. And I'll try a few different variants and we can talk about it next stream about which one worked the best. I might even check in on that when I do some more administrative type stuff later in the week. So, how does this fit into our ResNet our UNet is probably a good question. Step one, what we'll do, this one should still be running. Oh, we'll have a look at this just so we can see the images. So you can see here at the first epoch, it doesn't really learn anything useful. As we go, it starts to sort of blob more around the dog, starts to get more nuanced, and you should see that as we go on epoch to epoch, it's starting to pick up more and more of the dog as the pet class in this case. Now, mind you, this is the 50% mark. It's unlikely that everywhere around here is actually 0. It probably just hasn't crossed the threshold of being more than 50% accurate. Confident in it being a dog. But you can see the blob's getting bigger and capturing more and more of the dog as we go through the different epochs. And we'll have a look on weights and biases, but the dice coefficient should accordingly be going up to match. So we'll leave this running and we will check in on it at the end. And we'll check in on these features. We'll have a look at where they are at the minute. So they're still happily ticking along. All right, let's make a copy. Make a duplicate. And we'll build our ResNet. So the question that you might be asking yourself, we'll rename this to something a little nicer. We'll call this V1. I realized I 0 indexed the notebook names, but you'll just have to deal with that. So what we're going to do is we're going to look at replacing this conv pattern that we see a lot of times with different versions of the ResNet block. Because if you look at the ResNet block itself, you can see that it's in this original version, which is the first one we'll do, it is mimicking a conv with a couple of activations in there. So that seems like the easiest one to transform, and that should give us something we can pretty quickly implement. So because of the way we set this up last time, all we need to modify to make these changes is this conv block here, because the actual model itself is made up of a number of instances of this conv block module that we developed, and if we change the code for that, it'll change it in every spot. So what we had last time was a conv2d. Hey buddy, good to see you here again. I've chat on a different screen this time, so maybe a little slower to respond. We got conv, batch norm, relu, conv, batch norm, relu. And we need to transform that into something that is more ResNet-like. So, spoiler alert, I have done this before many a time, so I kind of know where we're heading with this. So we need to do a couple of things. Number one, we need to pull this relu out of the end of this sequential layer. The reason for that is when we do the addition in the ResNet block, we do it before the final activation. As just a matter of practice, that seems to be the way people do things. If you're interested in running some experiments, you probably could run it with relu on the other side of this addition and see if it makes a difference. There may be a good theoretical reason not to. We'll talk about some other implementations later, but to stick true to the paper, we need to pull that out. The other thing we need to do now, addition in PyTorch is pretty easy. You just do an addition. But as I discussed before, we've got these two variants of the ResNet blocks that we need to consider. We need to consider the scenario where the number of channels at the start and the finish is different. So in this case, 256 down to 512, and the number of channels stays the same. Now in our actual case, they always change. The number of blocks at the start of features at the start of one of these is always different to the one at the end. But we'll build a slightly more general version of this for the sake of it. So what we'll do is we'll call that, we'll say if the features in is equal to the features out. We'll call this identity. So if the feature numbers haven't changed, we don't need to do anything to x. So we'll use just a little lambda function here that just returns x. Otherwise, if the features have changed, we need a way to map x to its bigger cousin that has f out number of features. Here, what we'll do, similar to other areas, we'll just use a one-by-one convolution. Equals nn.conv. You know what? I'll just copy paste this to save us having to type this all out. Do a little bit of cleanup there. Get rid of this comma. So we're going to use a one-by-one convolution that goes from f in channels to f out channels. We're not going to do batch norm there. Padding technically won't change here because we've got a one-by-one conv, but we'll leave it in for consistency. So we've now got a few different pieces. If we look back at Excalibur, we've now slightly modified, let's get a little pencil here, our conv blocks, let me move that out of the way, to contain just this section here. We've got batch norms in ours, which they probably used but didn't put in the diagram. We've separated our relu out, and we've defined a function here which either maintains the number of dimensions and doesn't make any changes, or if for some reason this was, say, 128, boy, it's hard to draw with the mouse, What this would do is it would be a 1x1 conv, similar to what they're using over here, that had 128 features. There are different variants of this if you need to add additional features. Some people will, if it's a nice scalar multiple, they might replicate the features twice. They might initialize the extra features with 0, all sorts of stuff. I found in practice that using that 1x1 conv tends to give you pretty good results. Yes, you get a few more trainable parameters, but you're unlikely to suddenly overfit just because of that. So we've got all those pieces here. We've got the new updated sequential layers, the separated ReLU, and we got this identity function. We need to change this forward pass a little bit. We'll follow our pattern from last time of using Y as the sort of intermediate step. So first we pass it through these initial layers. We then we modify X, so we'll call it X underscore here, using that identity function that we used before. And then we will return Y. Oh no, we need to do one more thing. So we need to then add those two together. So we'll do Y equals Y plus X underscore. And then we need to return self.ReLU of Y. And so you can see this Y here is doing those comms. This is the mapping. We add them together to calculate the residual, and we return it. And that will give us, for all of these pairs of yellow arrows here, that's now been replaced with a conv block, a ResNet block, sorry. So if we grab this, I'll copy this image and see if I can just paste it in Excalibur so we can scribble on it. Paste this here. What we've done is we've added these residual connections sort of here. I guess it goes down to that blue arrow, and then one that goes from here to here, and here to here, etc., etc., which is good. Now there is of course, this variant of it, which is the bottleneck blocks. We'll put that together. We'll design one of those as well, just for the sake of it. They're really mainly useful when you've got a ton of layers. But the reason, or the time where you might end up with a ton of layers in a UNet variant is if you make the modification a little differently. So what we did is we said, okay, look, we've got conv anyway here. Let's replace that with a single res block. But what you might do sometimes, and if you've got a big data set, a complex data set, or the likes, you might instead replace this with a res block and then this with a res block, and you'd have two at each layer. So that conv block that we just modified, rather than having two convolutional layers, you might have two res blocks. And that can be helpful if you have a more complex setup that you need to, let's say instead of just dogs in background, you have 1,000 classes that you want to characterize, so you need a lot more features to be able to do it. I also pulled a couple of images from some papers around how others had implemented this transition from conv ReLU through to a ResNet block. This one I thought was a little odd, but also kind of interesting in that they moved the batch norm and the ReLU to within the ResNet block. So the final output of these addition blocks are non-batch normed and non-activated, which is fine because they add an extra convolution to the start, which means that you've still got the same number of convolutions. But where this has a real effect in the UNet setup is in these gray arrows. So in our setup, what gets shifted from this early stage through to this late stage is an output here. It's been through two convolution layers. It's been added together. It's had an activation and in our case a batch norm applied to it. In this setup that I found in a repository, what would get combined between layers is a non-activated version of that. So you'd actually be passing, just before this ReLU, you would be passing that across the network. Now, in their testing, that seemed to work pretty well. I haven't tried both. I can try both, and I'll leave some long-running experiments on both for the sake of it. But I think what I want to, bring up here is that a lot of this stuff doesn't necessarily have theoretical superiority, although it might in some cases. But as you're exploring how to implement, say, Resonant blocks in a UNet, you might say, well, hang on. Do I want to put the activations inside or outside of this edition? What do I want to send across the UNet, and so on and so forth? And typically what you'll do, if you've got the time and the GPU resources, is try a bunch of stuff and work out what works best in practice. A lot of machine learning is theoretical basis and then practical implementation. And you shouldn't be afraid to do that, especially if you're doing this in a professional context, because at the end of the day, unless you're doing ML research, your goal is some practical application, and you should be experimenting to maximize whatever it is that you're trying to do. But anyway, I digress. Let's implement this block, this alternative version, and then we'll have a look at how we might switch between them in our model setup. And then, as I said, offline, I'll run experiments with, A, B in a couple of different places, and we'll do a comparison next time, see which one did end up working best. And, we might use A over here on the way down, and we might use B on the way up. Or we might use A for the top couple of layers, and we might use B for the lower couple of layers where we've got high numbers of features. I'll try a few different setups, and we'll see what comes out best. Likely, what I'll predict, given the nature of the data set we're testing this on, is the differences are not going to be huge because there's just not enough lot of data in this particular PETS data set. So I'll probably start to work on getting a more complex data set. We might work on, Cocoa is huge, but it's got a ton of images. It'll take a long time to train though. So I'll set up a variant for that. Anyway, let's build our second ResNet block. That's our bottleneck block. So if we come back here, we're going to create a second module. Might as well start from the base that we have with this conv block and just pop it in here. Cool. And we're going to change this from conv to bottleneck. So what is different in the bottleneck block? So in the bottleneck block, there is a temporary reduction in the number of features. And then it comes back up to the same amount of features on this side, or whatever you want your number of output features to be. So to make this work, we're going to need to add an extra parameter to our network, and we're going to call this reduction. And that's going to be an integer. A 1 times reduction would be no reduction at all. 2 times reduction would be halving the number of features at the intermediate levels, and so on and so forth. Actually, that might get confusing if we're changing the number of features. So why don't we just call this fmid? So this will be the number of features in the middle of the network. So what we'll need to do here, just jumping back and forth, is number 1, insert a convolution that takes us down, a 1-by-1 convolution that takes us down to our mid-level feature space. So we'll make a copy of this. We'll put it here at the start. So we will have f in at the beginning, but we want to go to f mid. We want to do a 1-by-1 convolution, and that'll take us from, let's say in that previous example, 256 features down to 64 temporarily. We then want to do our normal 3-by-3, but in this case it's f mid in the middle. And then finally we have another, we got to change these. Another convolution, which will be 1 by 1 again, which does f mid to, where do we go? F out. Yeah, no, that's correct, but it's a 1 by 1. Now this is another example of where you might say, well, how do we do the implementation here? Because technically speaking in this one, the 1 by 1 convolution here goes back to the original size. So we're using a different sized output in our particular case. And I think, in the spirit of the paper, reading it from a sort of practitioner's point of view, the intention here is not to necessarily go back to the original size, but to go to the required output size. And you would then still have this sort of identity mapping, which is either no mapping or a change in the number of layers there. So without needing to do anything else, this should work if we put it into a network. Now, one thing that is going to make this more complicated, and this is a good chance to show how this might work in practice, is that based on how we want to configure our model, we either have intermediate layers with 2 different sized inputs, or we have intermediate layers with 3 different sized inputs. But when we look at our actual UNet model, we're always using 2 features when we define our conv blocks. Now, the way I would do this and get this to be, I guess, a little bit more flexible, perhaps at the cost of clarity, is we'd need to start abstracting some of this information out to function parameters. So you can imagine that rather than always use this hard-coded conv block, we might pass in which module we want to use for the conv blocks. We might pass in a flag or a string or an enum that then within this code allows us to pick between, let's say, a conv block and a bottleneck block. So how are we going to do that in this case? I think for the moment, what's going to be the easiest way? Well, I mean, I guess a third option, which is not ideal, but can also work if you're trying to think of how to make things a little bit more abstract, is we could add an f-mid parameter to this other module that just gets completely ignored, which would mean that we can always make use of 3 different levels in our ResNet. But what we'll do is we'll run this simple one first, then we'll start to tweak, maybe replacing some of these conv blocks with bottleneck blocks and ResNet blocks. And right now they're all this type A block because we replaced the conv block with this code compared to our original, which was just 2 conv layers. And what we might do is we might switch some of them to this B block, probably at the lower parts of the network where it makes sense to do something like this. But let's check in on our original run with the error fixed and see how it did, see if we can get some more useful images at the other side. So let's back to epoch 0. Slowly starting to pick up on the dog there. 6 or so epochs in. Look, it's starting to get there. I certainly wouldn't ship a model like this to production if it was mission critical, but really we're just messing around here trying to learn some stuff rather than worrying too much about this, how it performs on this particular data set. Another part of that is that in reality, I just picked a lot of these hyperparameters at random. You would likely want to tweak these hyperparameters a bit more, which is another thing we'll check why that config doesn't log properly. Anyway, let's have a look. So it's capped us on our displays, but you can see it is starting to actually do a pretty good job of picking up this one particular dog. Before I click this, because it doesn't actually seem to often show the continued output when I click it, let's just check back in with our weights and biases friend. So eval dice, which is our probably most preferred metric here, we're sitting at about 0.76. I don't know if you can see that on the screen. There's about 0.76 for this light blue line, which is the more recent one. So as far as dice scores go and segmentation models go, it's all right, but it's probably not the best we can do. That's for sure. Now, is ResNets going to be the magical solution to that? Probably not, but it might help us in that direction. We'll do a bit of other stuff later on, tuning some of the parameters to see if we can improve it more. So we'll go back into our original group and we'll let that run for a bit more. I might stop that early and rerun it after the stream, but let's work out why this config didn't log properly. Maybe you can't just set it as a dictionary afterwards. All right, well, let's try that. Let's just throw it in the init instead. So I'll update it here. We'll update it in our ResNet version as well. That's probably why it didn't log. All right, V1. Actually, let's go down here. Show more. And we'll have a look at... Stop the kernel. Click the message. And we'll have a look at where it got up to, because then we'll have a little bit of a head-to-head between these ResNet setups. So you can see it's sort of learning and unlearning different areas around this dog. It's where it crosses the exact threshold of 0.05. It's not completely forgetting. It's probably dropping to 0.499 in the intermediate layers. But we got up to 36 epochs. It got a good section of this darker part of the dog. Not so good in this sort of overexposed part of the dog. But that could give us a hint about where this model needs a little bit of work. And that's where things like adjusting the brightness or the contrast can be good forms of augmentation to help expose the model to more varied types of data. We'll save this one and we'll come back to unit 1 and we'll give it a run. And we'll see for the first few epochs if we get much difference. So we'll set up a slightly different grouping here. We'll call this one ResNet. And we'll add an additional config here to... I don't know if you can do this. Let's have a look at the docs. I want to just keep track of number of different variants. Yeah, it seems to want numbers. Oh no. Oh, data sets, key value pairs. Yeah, cool. All right. So what we're going to do is we're going to just track a couple of different variants so we can compare them. And we'll call this one all A to indicate that it's all block A or type A from these two A-B scenarios. We'll then try one that's all B and then we'll try a few different mixes, blend them together, see what one gives us about results. But number one, let's check our syntax. Oh, that's never a good sign when it hasn't saved. Okay, cool. Save it again. So the other thing I noticed after doing a few runs is that while I did do a manual seed here, there are other seeds that we need to set apparently because the image that it picks to display is not the same image, which means that it's shuffling the data set differently, which means that we get slightly different data every time. In reality, it shouldn't matter that much, especially as we're just testing stuff, but it means we cannot compare this same picture of a dog, which is, oh, maybe it does. Maybe it's something else that it doesn't. Uh-oh. Well, what do we do? All right, we got an error. Let's go. Ooh. Tried to allocate 128 meg of... Oh. That is because this kernel is still running and means it's probably allocated a bunch of GPU memory and we don't have extra to spare. So we will just save this. We'll restart the kernel just in case it's sad for some reason, and then we'll run that again. It should still fit because we haven't technically changed the number of... Oh, we've very slightly changed the number of parameters by adding these identity blocks, the one-by-one convolutions. But if we have a look in here at the last one that we ran and the system metrics, pretty sure the GPU memory... Yeah, look. Oh, that's not the memory, is it? Yeah, memory allocated was sitting at about 70%. It's not going to add another 30% to the memory usage, I wouldn't imagine. So cool thing here in weights and biases is you can group stuff and display either the aggregated groups or you can ungroup them and display everything, which is handy. I don't know how it groups them. You can probably tweak how it groups them. All right. Our kernel is reset, so now we'll run everything. We'll go back to here. We'll delete this run that never actually started. And we'll wait for it to start again. Just double check there's no errors. Hopefully this scrolling is not driving people mental watching it on screen. But we've got our dog friend here. So you can see compared to unit 0, which we should be able to open, but let's not run it so we don't run out of memory again. First epoch's always just sort of randomness. It's not really learning to segment anything, and that makes sense because it hasn't done any training yet. The initial loss, 0.85, initial dice is about 0.38, and you'd imagine that if we have a look at these, bit lower, about the same, and it just depends on what initialization we got. It should be after a couple of epochs at a pretty similar point. But we'll have a look here. So what I'll do so that we can compare them properly is we should be able to do this without actually deleting that one. Oh man, I just did that to work out which one it was and I totally forgot. So Still Bush is one that I ran the other day. We'll turn that one off because that was the one that had that bug. And now we can compare these two head to head. So this chart here displays the loss and the eval loss on the same chart. The dashed line is the eval loss and the solid line is the training loss. I'll just put a bit of smoothing on here so that it's a little easier to compare. But if you have a look at the ResNet paper that we were originally looking at, that's quite similar here to their thin line and thick line in terms of the error. So the bold curves are the validation error and the thin curves are the training error. Now they do some things here with the learning rate, which is why this stuff starts to step down like this. We'll look at that in the future. But to give you some idea about how to compare these things or how to graph them in the same way, I should say. All right, so a couple of epochs in, or just one so far. Our dice increases pretty quickly at the beginning. We could probably better initialize some of these things, but we got time. We got GPU resources. There's no point stressing over it too much. We'll just let it train. Starting to pick up the dog. And we'll have a look back here in weights and biases. about how it's comparing metric to metric. So, nice to know that the work that we've done is making a difference. We'll see where it tapers out to, but you can see here the dice score is higher, which is always a good sign that what we've done is worthwhile. It may end up just learning faster rather than learning better in the long run, but we'll see. We'll see as it learns. In terms of the losses, a little bit of difference here. The eval loss is lower there, which is another good sign. But keep in mind that anytime you add additional parameters to your network, you are likely to, lose the ability to head-to-head compare your loss values. You can get a pretty good feel for it, but that's why metrics like dice and things are so useful, because they give sort of a more independent way to characterize these things. Especially, if we're talking about regularization, so trying to remove overfitting, and we add something like the L2 loss, which is trying to reduce the average magnitude of weights in your network. Obviously, changing the network parameters means different numbers of weights, which can drastically change the loss because you're just optimizing a different group of parameters, which is why, unless you're really training two things that are very similar, the loss itself is not a good thing to compare head-to-head necessarily. So let's have a little check in our setup if it also managed to log those config variables. That'd be cool if it did. All right, good. So we got the batch size, we got the epochs, we got the learning rate, which I swear I made bigger. Have a look. Could be another change. Oh no, 1e -2. No, all good. It is the same. All right, that's good. So the reason that is good is it would allow us to, let's go, you can put some little notes in, allow us to add some different types of graphs here. So these panels here, you can see there's tons of stuff that you can put on here. One that people seem to like, I'm not necessarily a huge fan of them, is this parallel coordinates, which looks at typically different hyperparameters. Oh, my screen is stuck once again. Oh, it's been stuck for a while. I really need to work out why OBS is doing that. All right, so let me go back and just show you the things I was talking about. So the loss is down, that's better. Yeah, we can add these panels. So there's a lot of different things you can add here. You can create quite fancy reports. If you were doing this in a work context, you can create sort of a semi-live report. And you might, for example, on Paperspace, retrain your network every time certain GitHub repos were pushed to, and create a new and updated report that you could then pass on to your manager or a client, what have you. But we can have a look at some of these different things, like parallel coordinates was the example I was giving. You can have a look at batch size, not epochs, maybe learning rate, and then ultimately the eval dice. And you can have a look at how, if we were to change these parameters, let's say we did some runs with different learning rates, how these different hyperparameters map to different final values of the eval dice, which can be handy if you're doing hyperparameter optimization. I find these charts personally a little bit misleading because the order that you put your columns makes these charts look very different in practice. So they can be a bit hard to read, but they look good in reports, which might be of benefit to you. Now, the other thing which we didn't see, I showed before, but my screen was locked up, was that we now do have logging of the config parameters. So we've stored the batch size, the epochs, and everything else with our run, which means that if we're using a notebook here, which is fine, but if we were to want to recreate this this code, we can. Didn't even know. Oh, that's using a different thing. We could check it out, get to the same version of the repo, run it with the same hyperparameters, which is always quite handy when you're running dozens of these different training sessions for whatever reason. So we've let that run a bit. We'll have a look at the images. We're still seeing a slight boost in performance there, which is great. And we'll leave that to run. Now, the links are in the video description if you haven't seen them already. So if you do want to sit up and watch these, you're more than welcome to. Given the time, we've been on stream for how long now? About an hour and 10 minutes. We're probably not going to have time right now to do the different variants here, but depending on where I get to later in the week, I might jump on again and we'll do that. I certainly won't do it off stream. So when I come to do it, I'll just I'll go live and we can have a play around. And as always, these videos will be up on YouTube, so you can watch them after the fact. And if you are watching these and you want more of this sort of content, do all that generic YouTube stuff just to let me know that you find this interesting. Like and comment and all that good stuff. And thank you to everybody who's watching it. I hope you're getting a lot out of this. My goal here is to slowly level us up to some more complex work. So apologies for those gurus in the room that are eager for some more advanced stuff. We will get there, but we got to start from a base. I like going from first principles. Now let's see where we are with these images. So we'll do a little bit of a head-to-head. So Epoch 7, you can see here it's sort of got the bulk of the dog. We've got a dice of 0.67. If we look at our original unit and Epoch 7 as well, we can compare how those two things ended up. Epoch 4, 5, 6, 7. So you can see here 0.66 versus, boy, I really wish I didn't scroll back up to the top every single time. So it was 0.66 versus 0.67. There was a little bit less activity down here in this overexposed area, which seems to have been picked up in this run of the model. Now, is that because we added Resonant Blocks, or is it generally better initialization or whatever else? Hard to tell. We'll see how these things play out in the long run. But yeah, adding these more advanced features certainly can help your networks, and any modern variant of the unit, you'd kind of expect to have a lot of these bits and pieces baked in. So look, I think while watching logs is definitely fun, I think we'll leave it there for this evening. Hopefully you all found that interesting, informative, and is getting us on our way to more advanced configuration. And if you've got any questions, definitely leave them in the comments, and I will update the code in the next little while and get that up on GitHub if you want to run this on your own setup. And again, I think you can clone these notebooks if you're viewing it from Paperspace, so you could get up and running pretty quickly. Mind you, just to be totally transparent, I'm not sponsored or paid or anything by Paperspace or Weights and Biases or any of these other groups. They are good tools, and I pay for some of them myself. So I'm not here using them just because they're giving me money or anything. I think these are handy tools for machine learning, so hopefully you do too. I'll leave this running. I think I set the machine to turn off in 3 hours, so it's got about 2 hours left. We should see most of a run there. But look, otherwise, thank you so much for joining, and see you all next time.